Let me put that video on. Here we go. So this is kind of where, I'm kind of backtracking here a little bit from our last lecture, but I think that's reasonable. We were talking about solids and the 4 different types of solids: molecular, network, covalent, ionic, and metallic. We discussed the molecular and network covalent in quite a bit of detail. So today we're going to cover ionic and metallic. A picture is worth 1,000 words, isn't it? And, this picture, this figure here, I think really shows you the differences between these 4 types of solids, in that a molecular solid is individual molecules that are held together by intermolecular forces, whether they be London forces, dipole forces, or hydrogen bonding. A network covalent solid, I mean, the name says it all, right? It's a covalent solid. It's kind of like it's a giant molecule, right? All the atoms in a network covalent solid are held together by covalent bonds. Now, covalent bonds are a heck of a lot stronger than intermolecular forces. And so you can imagine that network covalent solids are going to be very hard, have high melting points and boiling points. Ionic solids are comprised of ions that are held together by the electrostatic interaction between positively charged cations and negatively charged anions. We'll talk about those today. And then finally, metals have basically a collection of nuclei. So the nuclei of these metals, since metals like to lose electrons, the electrons of the metals will be shared between all of the nuclei. Okay, and it's that electrostatic interaction between the nuclei and the shared electrons, which we call the electron sea, that makes a metal. And most metals are solids at room temperature, and so you can imagine that these metallic bonds, or this electron sea, is very strong, right? Metallic bonds are strong. But what else do we know? We know that metals can do things like can bend. A lot of them can bend quite easily, and there's a good reason for that. Well, I'm not going to spend a lot of time talking about molecular solids because I did this in the last lecture, and we talked about how water is an anomaly and that water in the solid phase is less dense than water in the liquid phase. Then we talked about network covalent solids, and the 2 examples that we looked at specifically were diamond and graphite. These are 2 allotropes of carbon, so just 2 different forms of carbon. And, what's the difference between diamond and graphite? Well, a diamond is found in something like a diamond earring, and the hybridization of all the carbons in diamond is sp3. So each carbon is held within, a tetrahedron. You can kind of see here, it's kind of tell that it's a tetrahedron. Anyhow, so a diamond, again, network covalent solid, all held together by covalent bonds. Now, graphite, the hybridization of the carbons in graphite is sp2. They're all trigonal planar, but you see that graphite is made of a collection of sheets of carbon, okay, that are all in the trigonal planar molecular geometry. But what holds these sheets of graphite together is not covalent bonds, is it? What holds the sheets together is intermolecular forces, and we know that intermolecular forces are much weaker than covalent bonds. And so, again, the sheets of graphite are held together by covalent bonds, and so they're very strong, whereas the interactions between 2 or more sheets of graphite are simply intermolecular forces, and that gives graphite some of its interesting properties. Okay, the fact that the sheets of graphite are in fact held together by only London forces. Anyhow, again, I'm kind of going over this quickly because we spent a lot of time talking about this during the last lecture. Let's move on and talk about ionic solids. And we spent a lot of time naming ionic compounds, right? We said that ionic compounds, generally speaking, come from a metal and a non-metal, or even more broadly put, a cation and an anion. We said that metals like to lose electrons and non-metals like to gain electrons. Well, ionic solids are non-volatile. Now, what does volatile mean? Volatile means something that has a low boiling point. For example, propane. You'd say that that's volatile. You open up a propane tank, the liquid propane in there, it gets converted into a gas very quickly. That's volatile. So ionic solids have really high melting points. Let's say you spill some water on the floor, and you come back a week later. Well, you only spilled a glass of water on the floor. The water is going to be gone, right? Because it's going to evaporate. If you spill some sodium chloride, which is an ionic compound, on the floor, and you come back a week later, is still going to be there because it's got a really extremely low vapor pressure. Or put another way, it's got a very high melting point, and it's got an even higher boiling point. Now, ionic compounds are actually non-conductors of electricity, okay, in the solid state. If you have solid sodium chloride, for example, a salt crystal, it's not going to conduct electricity. Why? Because in order for something to conduct electricity, we need to have moving charges, right? We have to have electrons that can move. But an ionic solid can be a conductor of electricity when it's melted. So that means if you have sodium chloride, for example, in the liquid phase, it will be a conductor of electricity, whereas sodium chloride in the solid phase will not be a conductor of electricity. And if you have sodium chloride or any other ionic compound dissolved in water, that's also going to conduct electricity. Sodium chloride aqueous, right? Why? Because then you have ions in solution. And remember, we have to have moving charges or mobile charges in order for electricity to be conducted. It says here, lastly, that many are soluble in water, but not soluble in nonpolar solvents like carbon tetrachloride. If you look at the structure of carbon tetrachloride, CCl4, and I'm going to draw the molecular geometry. It's a tetrahedral molecule. Okay, are there dipoles in carbon tetrachloride? Absolutely, there are. Right, I'm leaving out the lone pairs and the chlorines, but there are 4 dipoles that are pulling in equal and opposite directions, which renders this a non-polar molecule. There are polar bonds, but the polar bonds all cancel, and so this is a non-polar molecule. Whereas H2O is bent, right? It's got a bent geometry. We've got a lone pair in the back. We've got a lone pair out in the front like this. And so we've got dipoles going this way. And so we have a net dipole or a resultant dipole going this way. And so water is a polar molecule. Well, what kind of interaction are we going to have between an ion of an ionic compound and a polar molecule? We'll have ion dipole interaction, right? And we could write that down here. Soluble in water. Why don't we box that in and we'll put ion dipole interaction. And so if I have a sodium atom, or sodium ion rather, it's going to be surrounded by the delta negative of the oxygen, right? And if I have a chloride, for example, it's going to be surrounded by the delta pluses on the hydrogens. And we looked at a figure of that earlier on in this course, so that shouldn't be a surprise to you. But what about the strengths of ionic bonds, right? Ionic bonds are really strong, but some ionic solids are stronger than others. Well, the strength of an ionic bond is going to be related to Coulomb, which is the amount of energy that it takes to break that ionic bond is going to be proportional to some kind of constant K, which we call the proportionality constant, multiplied by the charge of the cation times the charge of the anion. So you could write this another way. You could say the charge of the cation plus the charge of the anion divided by the distance between the 2 nuclei. What's the summary here? The strength of the ionic bond is going to depend on a couple of things. The charges of the ions, the higher the charges we have, the stronger the bonds are going to be, and the sizes of the ions. The smaller that the ions are, the closer they're going to be together, or the smaller my denominator is going to be. And so the higher my strength of my ionic bond will be. What you need to know for your exams, and I mean, I'm talking every exam that you've ever written in this class, really, virtually all of them, is that you need to know that lattice energy or ionic bond strength is proportional to, so not even equal. You just have to know that it's related to the product of the charges of the cation and the anion. That would be good enough, divided by the distance between the 2 nuclei. Okay, and how do we determine that? We add up the radius of the cation with the radius of the anion. That brings us to metallic solids. Metals, if you look at the periodic table, most of the elements in the periodic table are metals, and most of them are solid. There are exceptions to that. For example, mercury is a liquid at room temperature. Gallium has a really low melting point, and things like lead are soft. But most metals are, in fact, hard solids. Now, how do we think about a metallic crystal? Well, we think about the lattice points as being occupied by metal atoms. So every lattice point is an individual metal atom that's held together by metallic bonds. Again, they have a range of hardness. Some can be soft, and most are hard. And they also have a range of melting points. But what do they have in common is that many of them are good conductors of heat and electricity. Why are metals such good conductors of electricity? And I went over this with you a little bit this morning. The reason why is because we can kind of think about a metallic crystal is looking just like this right here, where you have a collection of nuclei. So this is a nucleus, okay? Nucleus or nuclei have a positive charge, and the electrons kind of surround the metals. Why would that be? Because we know that metals like to lose electrons. They like to lose them so much that they'll even share them with a metal in proximity. And so if we have an electron, for example, say we have an electron here, it's going to be shared, all over the place. It can flow all through this metal anywhere. And so we ran over a nucleus there. I shouldn't have done that. But anyhow, you get the idea is that the electrons can move around. Oops, did it again. Anyhow, and so since the electrons can move around, this enables a metal to conduct heat and electricity very well. We call it the C of electron, or the electron C. Here are some different solids with different structures. Right? What do these compounds all have in common? Diamond, potassium, and manganese. They're all solids, right? But they're different types of solids, aren't they? If we look at diamond, it's a network covalent solid. It's just a bunch of carbon atoms that are all sp3 hybridized. It's all sp3 hybridized carbon. If I look at potassium dichromate, it's an ionic solid, isn't it? Potassium dichromate. We have the dichromate ion, and we have the potassium ion. Right? Potassium has a +1 charge, chromate has a 2- charge, and those are going to be attracted to each other. The electrostatic interaction. Finally, manganese, Mn, is a metallic solid held together by metallic bonds. Well, let's try a problem that gives you an idea of the kind of questions that we might ask here. It says, classify each of the following species as a molecular, network covalent, ionic, or metallic. Well, we have the answers here, but let's kind of discuss them. First one, tungsten. The reason we use the elemental symbol W is because of the name wolfram. Anyhow, tungsten is a metal, right? Tungsten is just a metal that you find on the periodic table. If you think about tungsten, it's a transition metal. It says note its position on the periodic table, so it's element number 74 in the periodic table, so it's a transition metal. So that tells us that it's going to be held together by metallic bonds. So tungsten is a metal. The next one is nitrogen dioxide. Okay, well, what kind of compound would this be? Nitrogen dioxide is comprised completely of nonmetals. Therefore, it's not going to be a metal. It's not going to be ionic because it's not made of ions. And it's not a network covalent solid because it's not going to be held together exclusively by covalent bonds. There are covalent bonds in the molecule itself. If I draw out the structure of NO2, NO2 is actually has an unpaired electron, doesn't it? Because it's got sorry, I'm doing my math wrong here. It's got 12 plus, it's got 17 electrons, right? So this would be the structure of NO2 that I have shown here. Actually, no, it exceeds the octet rule. Fix that. There we go. There's the structure of NO2. It's a polar molecule. So what's going to hold NO2 together in a solid, or what's going to hold it together is going to be intermolecular forces, right? So this is just going to be a molecular compound. Diamond is a specific example that we looked at. It's an allotrope of carbon, all held together by sp3 you know, it's just a bunch of sp3 hybridized carbons all held together by covalent bonds, and so that would be a network covalent solid. The next one is ammonium carbonate. So if we go to ammonium carbonate, ammonium is a cation and carbonate is an anion, right? Carbonate has a 2- charge. And so since we have a cation and an anion, that's going to be an ionic compound. And then the last one is fluorine. And fluorine is a nonpolar molecule, isn't it? Right? Fluorine is just held together by a single covalent bond, and it's nonpolar. Therefore, this species is going to be molecular. It's not ionic, it's not metallic, and it's definitely not a network covalent solid. So if I have a bunch of fluorine gas, it's just held together by intermolecular forces, which would only be London forces since it's a nonpolar compound. All right, let's switch gears and talk about crystal building blocks. So when we think about solids, we think about them crystallizing into definite geometric forms. Many times the naked eye can see the crystal. For example, if you've ever taken a piece of table salt and held it in your hand and looked at it really closely, you probably noticed it has a cubic shape to it. Well, crystals have definite geometric forms because the atoms or ions are arranged in a definite three-dimensional pattern. Now, there are several unit cells that we don't look at in this class, but there are three that you need to be aware of because metals crystallize into one of three unit cells that are shown here. The simple cubic, SC, the face-centered cubic, and the body-centered cubic. Now, a simple cubic is simply the 8 corners of a cube. Okay, if I just take, you know, everybody's drawn a cube at some point in your life. Okay, so if I draw a cube, and Mr. Dion is no artiste, I can tell you that. But if I just draw a cube like that, okay, 1, 2, 3, 4, 5, 6, 7, 8. Right, the 4 corners of the cube. If each one of those has an atom, that's simply, or that is called the simple cubic crystal. So simple cubic. If I have a body-centered cubic, so I'm going to skip the face-centered and go right down to the body-centered cubic. The body-centered cubic, it says it's the simple cubic plus 1 atom at the center of the cube. So it's exactly the same as the simple cubic, but you've got 1 atom in the center. So you've got something in the center as well of the cube. And then the face-centered cubic is like the simple cubic, but you've got an atom in the center of each face. So if I back up, it's like this. If you have an atom in the center of each face, where we go, atom in the center. It's like you've got one in the center of this face. You've got one in the center of this face, center of this face, center of this face over here, center of the back face, and center of the bottom face. So you've got an atom in the center of each one. Now, if you're like, Mr. Dion, your drawing's terrible. I can't tell you what's going on. Well, here we go. Here's something a little bit better. So again, the simple cubic, you see how we just have an atom at each one of the 8 corners of the cube. The body-centered cubic, we get an atom in the middle, okay, or an ion, depending on the type of compound. And in the face-centered cubic, you see how in every, like here's a face, for example. See how we have something in the middle there. And all 6 faces have an atom in the middle of it. Okay, so what I told you before we started the lecture today, I said what you need to know about this is how many atoms are in the unit cell. What's a unit cell? The unit cell is the smallest portion of the crystal structure that, if you repeat it over and over and over, will give you the full crystal structure. Okay, let me show you what I mean with the simple cubic. It's easiest to see here. Okay, if you were to slice a square out of the simple cubic, right? If you were to slice a square out of this and only take what's inside the box, okay? Nothing more than what's inside the box, it's not going to have all the stuff that's on the outside, right? It's not going to be in there at all. Only the things that are on the inside of the cube will be there. So this is what the unit cell will look like for a simple cubic, okay? This is simple cubic right here. You're going to have 1/8 of a sphere. Look at this portion here, and we can pick any one we want, but if you just examine like this portion right here, you see this shape right here? Okay, that's 1/8 of a sphere, right? Think, cut the sphere right in half, so you have a half of a sphere. You cut it in half again, and you cut it in half again. So how many of those 1/8 of a sphere do I have? I have 1, 2, 3, 4, 5, 6, 7, 8. So how many atoms do I have per unit cell? I've got 8 corners, right? So for the simple cubic, I've got 1/8 of a sphere times 8 corners. That gives me 1. So the number of atoms per unit cell for simple cubic is just 1. Now in the body-centered cubic, which is shown right here, BCC, again, I have 1/8. I've got an 8 here, 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 and somewhere in the back, okay? So that means I've got 1/8 times 8 corners, plus I have an atom stuck right in the middle of everything. So plus 1 more. These cancel out, and I get 1 plus 1, which is equal to 2. So for a body-centered cubic, the number of atoms per unit cell is 2. You can probably figure out the face-centered yourself. Look, I've got the 8 corners that are all colored in like what is that, fuchsia or red? I don't know. 1, 2, 3, 4, 5, 6, 7, and I've got an 8th one in the back, so that's 1/8. 1/8 of a sphere times 8 times, so that's 1. Plus, look, you've got 6 faces to a cube. Each one of those 6 faces has half a circle, right? So then you have 6 times a half. What if I have 50 cents? 6 times. What do I have? $3, right? So I have 1 plus 3, so that gives me a total of 4. And so the number of atoms per unit cell in the face-centered cubic is 4. The relationship between the side, and this would be like this is a side, this is a side, this is a side. So these are, this is a side, a side, a side. If you calculate the relationship between the side of the cell and the radius of an atom or an ion, the side length for a simple cubic is going to be 2 times the radius. If you do it for body-centered cubic, you're going to see that S, or the side, is equal to 4R divided by the square root of 3. And for the face-centered cubic, it's the square root of 8 multiplied by the radius. Now, you don't have to learn how to derive these. If you want to do it on your own time, be my guest. I have all kinds of notes here in my binder where I've done it, but you're never going to be asked to do that. Something else that's interesting, though, is if you look at the efficiency of the packing going from the simple cubic to the body-centered cubic to the face-centered cubic, is that the simple cubic has the most empty space. The face-centered cubic has the next most empty space, or sorry, and then the body-centered cubic has the least empty space. So if we just look at the total amount of empty space. Here's the relationship between the side of the cell and the atomic radius, if you need some help calculating it. Now, the geometry of ionic crystals is going to be more difficult to describe than that of metals. Why? Because in a metal, all the atoms are going to have the exact same size. Whereas in ionic compounds, if I compare lithium chloride and sodium chloride, well, the chlorides both have the same size, but a lithium cation is smaller than a sodium cation, isn't it? Why? Because lithium has a lower principal quantum number than sodium, or an easier way to put it would be sodium is further down in the group, right, in group 1A. So if you look at the face-centered cubic structure of lithium chloride or sodium chloride, the larger chloride ions form a face-centered cube with lithium ions in the holes, okay? Which is going to look something like this. So this is my lithium chloride. Whereas sodium chloride has the same face-centered cubic structure. However, since the sodium ions, this is a sodium ion, I need a pen that's going to work here. This is a sodium ion right here. Since that's bigger, chloride ions are pushed together, or pushed apart, and the face-centered cubic crystal is going to be slightly bulkier. Here's an example of a sample problem that I would ask, or sorry, that I have in my slides, but I would never ask this problem. So I'm just going to skip it.